Three body diagrams for the bucket when it's centripetally accelerating. As you can see, when the bucket is at the bottom, the force of gravity is facing down and the tension will be going upwards. When it's going to the side at this point, then the force of gravity is acting downwards as well, and then tension is facing towards the side. And then when it's at the top, the force of gravity and tension are always going down. As you can tell, the force of gravity always goes down in this case, and the tension is always facing towards the center. And in this case, the center is my shoulder, which is where the bucket is rotating about. Something else to note is that the force of at the bottom, the force of gravity is smaller than the force of tension. Tension would be larger because if they can't be equal to each other, because if they are equal, then that would mean that the object is accelerating linearly, and that would mean it's not accelerating centripetally, which is obviously not what we want.
So why doesn't the water splash on Ivan at the top? Well, at the top, there's only the force of tension and the force of gravity acting upon the bucket. The water, however, will have inertia, which is a tendency to continuous motion, and in this case, it'll be to the left. If we look at the water without the bucket, we'll see that it'll follow sort of like a projectile motion, and the path of the water has to be greater than the path of the bucket, because for the bucket to contain the water. Otherwise, the water would fall on Ivan. Also, at the top, the force of gravity is greater than the force of tension. We sort of made a mistake on the last video.
So we're going to be solving for the minimum speed to get the water to stay in the bucket. So we know that there's two forces acting on the bucket. There's the force of tension and the force of gravity. So we know that the vector sum of the forces is equal to the tension plus the gravity. This also equals the mass times centripetal acceleration. So the force of tension is also, so there's a force of tension plus gravity, force of gravity, which is equal to mass times gravity, and this equals to mass times the centripetal acceleration, which is also radius times omega squared. So at the top, the tension would be 0, because we're calculating the minimum speed, so the tension would be 0 plus gravity equals mr omega squared. And then so we just solve for, we're trying to find angular acceleration, right? So so we divide both sides by m, we cancel the m's out, then we look for gravity equals r times omega squared, then do some more algebra, and then we square both sides, and then you get omega equals the square root of graphs over the radius. So we have the square root of 9.81, which is the force of gravity, and then divided by the radius, which is the distance from here to the center of mass of the bucket, and that is equal to around 2.96. And yeah. And so it would be 2.96 radians per second.